Okay, common logarithm, it's not that we don't care about you, but it's time for us to start seeing some other bases. If there is a base specified, like we see in this subscript right here, that replaces the 10 that we would use in the common log. So we can see in our exponential expression, we write in a base a, whatever that number specified might be, and still ask ourselves, if I'm trying to evaluate log to base a of x, it's the same thing as trying to answer the question, if a is the base and x is the result, what is the exponent? So in this first example here, log to base 2 of 8, what I'm asking is, my base is 2, what is my exponent to get a result of 8? However I would fill in this box is how I evaluate the log. I can see that 2 cubed is equal to 8, and therefore the log to base 2 of 8 is equal to 3. In this next example, the base is 3. I'm asking myself, what power would I raise 3 to get 1/9? I want to think about this in 2 steps. The first step is, just in order to get the reciprocal, in order to turn this into a fraction, the power has to be negative. Negative powers are what make the base take its reciprocal. Then to get from 3 to 9, I would need to square it. So the power -2 takes care of the reciprocal and the squaring. And so the log to base 3 of 1/9 is equal to -2. Finally, log to base 8 of 1. 8 is my base. I'm asking what is the power to give me a result of 1. And this is starting to feel more familiar probably. Anything to the power 0 is equal to 1, and therefore the log to any base of 1 is equal to 0. It doesn't matter what the base is. This is always going to be 0. Another base that comes up frequently that is not specifically written into the log is base e. So we call this the natural logarithm. We've already seen common log where no base is specified. We've seen log to base a where we write in the base as a subscript. The other situation is natural log, and that is abbreviated ln. It is implied base e. So when we see an expression like ln of something, we know that it's base e. And therefore, to evaluate it, I would automatically start with a base of e and say, what is my exponent to get me this result? Of course, I would fill in a 5 there, because e to the 5th is inarguably equal to e to the 5th, and therefore this answer is 5. I can answer a general question about a log with a as the base, even without specifying a number. As long as I can answer the question, what would I raise a to, what power would I raise a to get 1 over a to the 5th, then I can evaluate it. So I know that this power would have to be negative in order to get the reciprocal. It would also have to have a 5 in it in order to get that power of 5. So this is equal to -5. Looking at 2 more examples now, we have log of the square root of 10. Again, we don't see a subscript written, so this is an implied base 10. And we can say 10 to what power would give me the square root of 10? This is where we have to remember our rational powers, rational exponents. The square root is the same as the power 1/2. So I know that that log has got to equal 1/2. The power 1/2 is the same as the square root. Same idea here. This is a natural log, so I know it's base e. And I again ask myself, e to what power would give me the square root of e? Same question, right? Same answer. e to the power 1/2 gives me the square root of e, and so this answer is also equal to 1/2. Some important inverse properties about exponential and log functions are written here, and the first one is pretty easy to understand. The second one takes a little more getting used to, but both of them come from the fact that the exponential function to base a and the log function to base a are inverse functions. Now recall from the definition of inverse functions that the way they work is if I start with x and I apply a function and then its inverse, I should get back x. In this case, what I'm doing in the first example is I am applying an exponential function first, and then I am applying a log function to the result of the exponential function. So I get back that same x that I started with. In this second example, I'm starting with x, and I am first applying a log function to x. I am then applying an exponential function, so I should get back that same x that I started with. Now, the first one is fairly intuitive because this mimics the way that we evaluate logs. Log to base a of a to the x is just saying, I would raise a to what power to get a to the x. I can see that I would fill that in with an x, and therefore the result is x. So this one just mimics the way we evaluate logs. It's not very difficult to get used to. The second one is much more difficult to get used to. And I like to just put in some numbers to see it with a numeric example and hope that that makes it a little bit more comfortable. So let's suppose that we're starting with a base of a of 5. And then the bases here have to match, so that means I have also a log to base 5 of, let's say x is 25. If I were to just evaluate this using properties, using order of operations, I would first evaluate the log to base 5 of 25, and this part is equal to 2. So I am now going to take 5 to the power 2, which gets me 25. So I can see that the number up here matches the result. I started with 25. I took the log to base 5 to get 2. I then raised 5 to that power. I can see that I get back to that 25 again. So this one we just have to get used to looking for those bases matching. But there has to be nothing in between at all. It just has to be a simple base to the power of a log. So looking at this first one down here, we identify that the bases match. We have a base of 5 raised to a power that is a log to base 5. So we know that this is a composition of two inverse functions. 3 is where I start. I take a log to base 5. I then exponentiate with base 5. I should get back where I started from, and therefore this must be equal to 3. Next example, I have something that's more like the first form. The exponential function is on the inside, and the log is taken on the outside. So this is where I would say I have a composition of a log and an exponential. The bases match. This is simply x plus 1. The log will undo the exponential, and we will get back what we started with. In our very last example, again the bases matched. They are both base 10 because this is a common log. If there's no subscript written at all, then it is an implied base 10. So I have matching bases. This is an exponential composed with a log, and they undo each other, getting me back that same x squared that I started with.